I want to make a short video about characterizations of being an open set on the one hand, and that of being a closed set. Now, I will state these theorems and prove some parts of them that I think are the most interesting. And you can prove the rest now, or read the rest. Now, the first about when is a set open. It's important to have these theorems about when sets are open because you don't always want to use the definition of an open set to prove that something is open, but instead you want to use some theorems, and that makes your life a little bit easier and also gives you a firmer grasp of what it actually means to be open by relating it to other concepts that we have defined. Now, a subset of X is open if one of the following equivalent conditions holds. And these are equivalent for being open. So A, for every X, there exists delta, such that this is Bx delta isn't contained in omega. This is the definition that we have used. B, omega intersected with its boundary is empty. This is often used in calculus and other classes to define openness. And C, that the interior of omega is equal to omega. So these are all slightly different statements, but they are all actually saying the same thing in different ways. And just like in the video on adherence and some terminology, to prove these, one would have to prove A implies B, B implies C, and then C implies A, because this would show that these are equivalent to each other. Now, these are all very similar proofs, so I will focus now on only one of these, A implies B. So we are saying that if for every point in the space or in the set, there exists some radius, positive, such that the ball of radius that is contained in omega, then this is the same thing as saying that no point on the boundary is contained in the set. Okay. So let's prove this. Let's assume the assumption that for every X in omega, there exists a delta positive such that the ball of radius delta is completely contained in omega. And suppose, now there are different ways one could go about either contrapositive, but let's argue by contradiction. Suppose that the conclusion was false, that boundary of omega intersected with omega would be not empty. Well, then there would exist some point inside it and, well, it would belong into omega and it would belong into the boundary omega. Well, because it belongs into the omega by the assumption, we would get that no matter that there would exist a radius delta positive such that we take the ball of that radius and it's contained in omega. But being on the boundary means that we also have that no matter the radius that we choose, the ball would intersect omega in a non-empty way, and the ball would intersect omega complement in a non-empty way. So this is a statement for every, that's the statement there exists. So let's try to combine them in some ways to obtain a contradiction. Pick R is equal to delta in the second condition. Then BYR intersected omega complement is not empty. So there exists a Z in omega complement such that Z is inside BYR, and because Y is equal to delta, this is equal to BY delta. And the delta here came from the first condition. So we use the delta here. So Z belongs also here, but then as BY delta is contained in omega, we get that Z is actually in omega because Z is inside the first set. Therefore, it's in the second set because it's a subset of that. So we get that Z is in omega and Z is in omega complement, but this is a contradiction because you cannot be a set element of both a set and its complement. Now, the other parts would be very similar to this and use similar logic. You write out the definition, you do some simple steps, possibly dividing into cases, and then you get your conclusion. Now, but we only proved A implies B. Now, let's look at when is a set closed? What kind of conditions can you use, and how does it relate to what you know from before? So we use the definition that no matter the sequence of points that you choose from the set, if that sequence converges to an X, then that limit point has to also be in the set. So this was our definition. And this theorem that says that the following are equivalent. And for a closed, well, for any set, they are equivalent. So we can actually remove this. Just means that these are closed in both cases. So we could add a condition here that's closed, but not right here. So any set, the following are equivalent. And the first means closed, so therefore the second also is a definition of closed. And this means, in colloquial terms, the boundary is contained inside the set E. So again, let's prove A implies B. So assume A, and now I don't repeat it because we are quite close to the statement, and prove B. Well, we have to prove the inclusion, so we have to pick a point, X, in the boundary of E. Then X is in the boundary of E. So for every radius, positive radius, the ball BXR intersects E in a non-empty way. So it intersects in a non-empty way. So now using the same trick as in the video on adherence sequences, then if we pick different R's going to 0, we can find a sequence that converges to X. So for each n in natural numbers, the ball of radius 1 over n intersected E is not empty. So therefore there exists an xn. We can pick xn inside bx 1 over n intersected E, which is a non-empty set. But now xn is in E for all n. And dxn to x, the distance is less than 1 over n, and is always non-negative by the definition of a distance. So limit as n goes to infinity of the distance xn to x is equal to 0. And by definition, limit as n goes to infinity xn is equal to x. By our assumption, this means now this is a sequence of points in E that converges to x. By assumption, x has to be an element of E. We're done. The other direction is very similar to this as well. Yeah. But I will leave the other direction, B to A, as an exercise.